Thanks a lot. Thank you for inviting me on this particular international faculty development program, and to address the august audience over here, including faculty, students, and the practitioners of applied mathematics and machine learning and AI is really a charm. So today I am going to deliver a talk on dimensionality reduction and its applications in science through a lens of visual mathematics. So let me start the whole presentation with famous quote, which I really revere, from Paul Dirac. He said once in his one of the article in 1953, later published in 1963 in Scientific American. He said, one could perhaps describe the situation by saying the God is a mathematician of a very high order, and he used very advanced mathematics in constructing the universe. Our feeble attempts at mathematics enable us to understand a bit of the universe, and as we proceed to develop higher and higher mathematics, we can hope to understand the universe better. This is also the concept which is very much in line with the best of the best Nobel laureates, Abel Prize winners in the field of mathematics and alike. So if you see that there are certain components which I have highlighted as bold, it's all are highlighting to the very key fundamental theme of this international conference today, which is that what is the importance of mathematical modeling and its application in real science. And as I highlight application here with a key connotation that as the whole world is now moving towards that, we need not to only work on research and development, we have to work on research and technology. There should be a product which we can realize if possible, definitely. So in that particular pursuit, the key idea is, which I'm going to present today to all of you, and we both and we all are going to ensure that we're going to enjoy this whole topic of higher dimensions and the God's universe. So let me begin the part of the presentation with two particular quick questions. The one is, can you tell me what is the fourth dimension? Can you visualize the fourth dimension? Second, the person over here on the right bottom corner is Carl Pearson, who is known as father of mathematical statistics. Can you tell me how Carl Pearson is related to dimensionality reduction? Some of the answers are hidden in the presentation, so I encourage you to go through the presentation along with me and be inquisitive and stay curious. We can have a conversation later on through my LinkedIn. Otherwise, some of the answers are hidden over here. Let me begin the presentation with today's agenda.
Sir, excuse me, sir.
Yes, please.
So participants are saying that your voice is not that very clear. Be a little louder, sir.
Is it better now?
Yeah, okay. And on your camera, sir. Camera, let it be in on mode, sir.
It's on.
Yeah, it's on only. Only now. Okay.
I don't know. I mean,
sir, voice is not clear, sir.
Okay, is it better now? Hello?
Okay, voice is better now.
It is much better, sir.
It's better only.
Better.
Okay, thank you. You can let me know if there is any kind of thing need to be improved. All right, so the agenda of the presentation is, first I'm going to talk about going to inspire the audience over here to motivate you enough that why we should learn about dimensionality reduction. Then we'll briefly go to the second part of the presentation, that is dimensionality reduction and its basics, and few key algorithms which we use in day-to-day life, such as principal component analysis, commonly known as PCA, then LLE, the nonlinear dimensional reduction algorithms, and also Tisney. Then in the third part of the presentation, we are going to go through the applications of dimensionality reduction in science and few live demonstration of the visual mathematics. Later on, as this is a faculty development program, also I would like to share a few recommendations from my side to the audience over here with the context to have better future research and technology research. As I said, we need to move from research and development to research and technology, right? All right. So let me start the first part of the presentation, that why should I learn dimensionality reduction? This is the key fundamental question which always keep your mind boggled, that why do I have to learn this? As an engineer, as a good practitioner, as a good scientist, we always have to understand and give the answer to ourselves faithfully, that why I'm doing this, why is this thing existing, right? This quest is behind that, why science is really flourishing and the technology is developing around us. And the second part is that, why is it really important? So let's try to address these questions. The first one is that from the perspective of data visualization, it is critical to get into dimensionality reduction. The target is to find the smallest subspace of an n-dimensional ND space that keeps the most information about the original data, and we would like to do the visualization of it from the context of the descriptive statistics, and likewise to visualize it, because that's the human nature. We would like to see our data and then make inferences out of it. All right. The second key critical thing why we have to get into dimensionality reduction and why we should learn as a student, as an educator, we have to teach and we get into practice is the curse of dimensionality. So this is the one key phrase. Now there is definitely a counter phrase which is very much famous in the applied mathematics community, which is known as blessing of dimensionality. But from the perspective of dimensionality reduction, it is critical that when the feature size in machine learning or the number of random variables keeps increasing, then the space also increases so fast that the available data becomes really sparse. And handling the sparse data is one of the key challenges in any of the domains. Sometimes it is beneficial, but most of the time, from the point of context of curse of dimensionality, it is something which we have to deal with seriously. So the tool and the technique is the dimensionality reduction, which we'll go through in detail in the rest of the presentation. The third is the geometric interpretation and visual inferencing, which is very close to me because as an engineer and I'm practicing as a scientist. So from that two particular facets, I always would like to understand, and the key notion I live with is to make complex easy, right? So from that perspective, the key idea is it possible to have these particular equations in front of me and use the mathematical concept and produce that in a geometrical sense so that I have a better intuition around it? Can I have a visual inferencing using visual mathematics? That's the idea, right? So most of you will be already aware of one of the key critical geometrical construct. It's known as Tesseract. It is a fourth dimension analog of a cube. The cube, we all know, it is, so if you see on the left-hand side, this cartoon shows, if you see the inside of it, it's like a cube, right? And the outer part is also like a cube. Now, if I put one cube inside a cube, and that is particularly very famously known as Tesseract in the geometrical connotations in applied and pure mathematics. So the tesseract is to cube as the cube is to square in 2 dimensions. Yeah, and the tesseract is a hypercube in R4, like we generally deal with R3 for visualization. Also, it is a 8-cell or octahedron. So you shall be able to observe over here on the bottom right corner the visualization of a tesseract, which is in a static mode over here on the bottom right, bottom left corner. So here you see a 3D projection of the tesseract performing a double rotation about the orthogonal planes. And if you see over here, you will be really mesmerized to see the 4th dimension is at its play, right? So this is one of the key things which is available in science by the purest language, that is mathematics, that we can visualize the fourth dimension so well. And if you are a string theorist in physics domain, then definitely you would like to play with more dimensions than 4D. But the key idea is, as the number of dimensions keeps increasing, can we still visualize that and mesmerize? It's not only for the illusion as well as for getting yourself really cherishing the whole idea of 4 dimensions, but it's very critical to understand that how we can understand the visual inferences from the high dimensions. So as the dimensions keeps increasing, as I said, then we cannot visualize it so well, and then we have to get into dimensionality reduction techniques, which is the key idea of the presentation today. So now I'll jump into the second part of the presentation. Do we have any questions over here? Professor Geeta, is there any questions from this?
No, sir. No, sir.
All right. I want to make it more interactive. That's why I'm asking in between. Otherwise,
Okay,
definitely
sir.
at the end we can ask.
Even in the chat box, I'll just let you know, sir.
All right. So now let's enter into the second part of the presentation. That is the basics of dimensionality reductions. As I said earlier in the agenda, so one of the key critical algorithm, which is famous in the community in the machine learning these days, or in the applied statistics also, as I'll be also discussing. So principal component analysis is not the product which came out from machine learning or AI community, right? Or it was developed, it was invented long back, almost a century back. If I have to say the precise number, it was devised in 1901, and definitely it went into different new forms, but the fundamental algorithm was developed in 1901, right? So never get mesmerized by the new analogies and the new terms, because the key thing always holds true. The old is gold. So there, then we will going to briefly talk about the nonlinear dimensional reduction techniques, the Disney and the LLE. So let's start. What is dimensionality reduction? In statistics or machine learning, dimensional reduction or dimension reduction is a process of reducing the number of random variables under consideration by obtaining a set of principal variables or components. We'll discuss about what are principal components, so don't worry if you're not aware of. Let me give you an example. So let's take a case that we have 53 blood and urine measurements or samples, which we call as features. Generally, this is a common term in machine learning. So from 65 individuals, yeah? So if you see in this particular Excel cell plot, the columns are the features, yeah? And the rows are the instances, that is from every individual. So we have 65 rows and 53 columns, yeah? Or 53 features. The question I'm asking is, or you should also ask, how can we visualize the measurements, right? And this is the very simplest lower dimensional case I'm talking about, which is we generally deal with, right? We can definitely, we are going to extrapolate that in hundreds and thousands of order today itself. The next question is, it's very difficult to see the correlation between those features, yeah, visually in this particular format. Let me show you, pictorially, all these samples. When we do the spectral format analysis, then the 65 pictures, when we plot for the 65 instances, one for each person, this is how the data looks like. Messy, don't have very key critical information which we would like to extract and want to pass on to the individuals. Similarly, when we do the spectral analysis for 53 instances or features, 53 features, at that time we get something like this, where this plot is one for each feature. Doesn't make sense, right? Only I get some kind of a wobble trend. Let's see, can I have some other kind of variation into the visualization? Can I look into the bivariate plot, 2 particular features at a time? or trivariate, three variables at a time, trivariate. But now I'm asking the question which I really want to excite you earlier in the motivation slide, that it was really mesmerizing to see, to work with Tesseract. But what about high dimension? I'm talking about 53 dimension here. So is there a better representation that than the Cartesian coordinate axis in this particular scenario? Is it really necessary to show all the 53D? What if there are strong correlations between some of the features, then ideally we can take them off? How could we find the smallest subspace is the key critical question I'm asking over here. Yeah. How could we find the smallest subspace from the 53 feature dimension subspace, the space that keeps the most information intact about the original data? Is there any answer? So yes, there is a solution. And one of the solutions when the data we would like to extract and transform using linear operation is the principal component analysis, PCA. Let's look into that a little bit deeply. Now, for the level of human interpretation, easy human interpretation, which is the visualization, we can do that in Cartesian coordinate. We are very much familiar with three-dimensional spaces, 3D. Let's look principal component analysis, PCA, in 3D. Look at this data on the bottom left corner over here. Now here you see that the data is scattered in the 3D space. Now when I'm going to put the whole data into two principal components, where the x-axis is the PCA1, which is known as principal component 1, and y-axis is the principal component 2, right? And over here, I'm going to discuss on the principal components, so please stay tuned and just digest this for a while, who don't know. So this particular chart shows you the variance, that how much the data is dispersed, right? So this is the x, y, and z axis, the original coordinates, right? And these are the principal component axis. Now, please appreciate, now over here, we didn't do the operation using the principal component, but let's do that operation now. When we have done the principal component analysis operation and the axis has been turned, now if you see over here, whatever we have, right, the data, so the majority of the data is along the red coordinate, red line over here, yeah? So now if you see the dispersion in the principal component, the variance is maximum, unlike what we have earlier, yeah? And if you see in the original data representation using the Cartesian coordinate axis, x, we are getting even better variance. So we can get the compression of the dimensions, we can reduce the dimensions, we can do the dimensionality reduction, and still get the maximum amount of information from the original data. So this is the whole essence what we are trying to target over here. The PCA transformation ensures that the horizontal axis, PC1, right, has the most variation, which is represented over here. The vertical axis, PC2, which is, so all the principal component axes, mathematically, they are all orthogonal to each other, right? And they are ordered so that the maximum variance is collected in the first principal component and then so on. We'll discuss about the mathematical connotations very soon, but this is the whole essence I would like to let you appreciate. Obviously, PC3 is the one we are going to drop with the whole idea of reducing the dimensions. So now here we are going to obtain 2 dimension from a 3-dimensional space. Yeah. Now let's see that what is the mathematical model behind the PCA algorithm. So one of the key idea that you have to please appreciate is that the eigenvectors and eigenvalues are at its play when we are going to extract the information for the PCA algorithm. Yeah. So I'll not go into the detail in the interest of time. And there is one particular lecture which is available on YouTube. I have delivered that last month. So you can watch that to understand the complex eigenvalues and their intuition in the application of science. But these particular idea we are going to use in PCA as well. Let me tell you how. So now let's say we have a data from x1 to xm. We should compute first the sample covariance matrix. So this is the definition of the covariance matrix, where the mean is represented over here, x by x bar. So the PCA basis vectors, the eigenvectors of the covariance matrix is what we are targeting. The larger the eigenvalue, the more important is the eigenvector, right? So if you see that, this is what I was emphasizing again. So if we know the value of eigenvectors, then we can move towards the PCA algorithm, and its mathematical modeling is making a very systematical sense to us. So to give you a quick brief about that, what is the physical intuition behind the eigenvector and eigenvalue. So please focus on the cartoon over here on the bottom right corner. This is the two-dimensional Cartesian coordinate system, where horizontal axis is the x-axis and the vertical axis is the y-axis. And the original vector for the equation ax is equal to lambda x, which is the eigenvalue problem. So I have the x vector, which is represented by this bold red arrow, right? So now over here, now when I do the matrix operation over this vector, that is x is the vector x is operated by the matrix A, then if I get the only scaling of the vector x, no rotation, yeah, only scale up or scale down. In this particular context, it is scaling up. Then only the vector x is known as, it is a eigenvector, and the value by which it got scaled up is known as eigenvalue. And here that value is lambda. So now after the matrix operation, the x becomes lambda x, which is the right hand side of the equation, and it got scaled by lambda, and now the coordinates becomes lambda x comma lambda y. Yeah. Now let's come back to the PCA. So now when we have the eigenvectors of the covariance matrix, which we can do it very easily, fortunately, now using all the scientific computational tools like MATLAB, Mathematica, Python, and likewise. So we can use the standard linear matrix algebra technique, that is singular value decomposition, SVD transformation. And we can decompose the training set matrix X. And the training set matrix X, assume that what I was talking about with the 53 instances and the 65 sample test. When we have 53 features, and 65 sets the rows. Yeah. So consider that is the matrix X, which I call as the training set matrix X, into the dot product of three matrices, U, covariance matrix, and V transpose, where V transpose contains all the principal components that we are targeting. And it can be done very, hello? Okay. So it can be done very easily from a scientific computation point of view in Python. So I'm giving you some snippets of the codes from the Python itself, where there is a library in Python or in Fortran or in other computational computing languages. It is known as subroutines. So there is a library known as scikit-learn. Yeah. So we can import the scikit-learn and then import the PCA, the principal component analysis, which is already, with all the assumptions of centralization, everything is taken care already. So we just need to say that, what are the number of components, the dimensions I want to preserve, and then we can get the answer. Moving ahead, the key question which comes to a scientist is that, no, I have 53 dimensions. I don't want to reduce into 2 or 3 just for the sake of visualization. But what is the optimal number of dimensions which I really would like to reduce so that my content, the information should not be lost. At the same time, I shall be able to still reduce to the optimal dimension, right, which I can work with even further after, like for clustering, for regression, or for other statistical information I would like to extract from that data. So yes, that's already been addressed. And that is like, what should be the right number of dimensions I should really work with. So instead of arbitrarily choosing the number of dimensions or to reduce down to, say, 2 or 3, it is generally preferable to choose a number of dimensions that add up to a sufficiently large portion of the variance, which we saw that in the earlier PCA in 3D, that the variance should be maximum, right? So generally, the thumb rule is that the variance should be preserved such that the 95% of the variance should be intact. And this, on the right-hand side, the snippet of the code shows you that if you really want to preserve the variance by 95%, that's very easy to do that in scientific computation. So we just need to mention that number of components is equal to 0.95, and then 95% of the variance will be preserved, which will going to give us, which is known as explained variance. It's going to give us a plot that if we plot the variance on the x-axis, where 0 to 1 is the percentage of the variance we want to preserve. In this case, for example, 0.95. So this is the target. And on the x-axis are the number of optimal dimensions we should work with so that we can attain the dimensionality reduction. At the same time, ensuring that the whole information should be intact as much as possible without losing any critical information in the original data. So if you can see over here that for 95%, so we need to really look into 150 dimensions, or if we go for 100 as well, then we have enough amount of information, around 90% of the variance we can still preserve. So imagine that if you have 100 or 1,000 features, it's a huge amount of matrix operations you need to do. It has a load on the infrastructure, it has a load on the optimality and different routines you need to work on, and it's time consuming where your boss, where your, the work for the research which you really want to do and accelerate. The dimensional reduction is really at your service, if you have to say so. So now we have seen that why we do PCA, right? What is PCA? The key, the crux of it. Little bit of matrix algebra behind it. The importance of eigenvalues, the largest eigenvalue, the largest eigenvector with the maximum variance it should preserve, and then what is the optimal number of dimensions we should work with by the explained variance, right? And similarly, at the same time, we were also going through the snippets of the hands-on in the Python, right? So there are definitely, we should not restrict to the PCA, because PCA itself has its own limitations. It is good for linear type of transformations, but in itself, in the PCA, if the data keeps coming at a continuous stream, right, then the PCA doesn't work as it is. Well, then we have to work with something what is known as incremental PCA, right? Then there are other very computationally beautifully smart techniques, I would say, is known as Kernel Pca, where you can optimize along with the grid CV type of, the CV stands for the cross-validation techniques. You can work and tune your hyperparameters. Hyperparameters in a mathematical sense are basically the coefficients of your, let's say, a differential equation which you want to really work with, right? So then there are other techniques which are good for nonlinear dimensionality reduction, unlike PCA, which is good for linear dimensionality reductions. And the classical test function is the Swiss rule and the S-curve type of data, which have, where the PCA really don't work well, but the other techniques such as locally linear embedding, LLE, MDS, they work quite well. And one more technique here, which is quite famous, is LDA, which is known as linear discriminant analysis. It is actually a classification algorithm, but it as the algorithm is designed in such a way that it helps also in reducing the dimensions of the feature set. So, but the key critical, and I must say that it's one of the best and the latest dimensionality reduction technique is the t-SNE. So the full form is T-distributed. This is a T-distribution usage in this algorithm. Stochastic neighbor embedding. So it was developed by, also known as in the third wave of AI, which we are going through by the father of AI, that is Professor Geoffrey Hinton. So in 2010 or 12, I guess. So t-SNE reduces dimensionality while trying to keep similar instances close enough and dissimilar instances apart. Quite useful when we are doing the natural language processing type of work, because it is going to be very much useful in the visualization, in particular to visualize clusters of instances in high dimensional space. Let's look into that a little bit more deeply. So now over here, you see that there is a data which has so many information carrying features. Yeah. Now, when we play and work with t-SNE, unlike PCA, which is the linear transformation technique, the t-SNE takes care of this kind of cluster, and it makes the information into certain segregations which are known as clusters, representation of all these particular data instances, right? At the same time, it reduces the dimensions, and the third benefit we get is we are going to get a visualization of so high dimensional data in a cluster form. So we can still work with that and ensure that what actual information we really want to work with, right? And as I promised you, so we are not going to work with 53 dimension or 2 dimension or 3 dimensions. I'm going to give you the real information from the author who developed this, whose paper is listed over here. So where they worked with data sets which scales up to 30 million. This is like huge amount of data sets. So you play with this, and some of the snippets I can deliver to you if you, work with me in the LinkedIn. I'll give you the information later on. So let's quickly go into the second part of the presentation, that is application of dimensionality reduction in science. So here I have listed some of the applications of dimensionality reduction. So one we saw obviously is data visualization, critical from the perspective of statistical significance test, descriptive statistics, or EDA, which is famously known as exploratory data analysis. Data compression, if you really want to compress your huge amount of pixel data. These days, for example, in computer vision algorithms, we have we need to take the picture, and if it is a grayscale picture or a color scale picture, we need to split that into certain pixels, and then work with the AI algorithm, that is CNN, convolutional neural networks, and other variants of it. There, we really want to compress the data, ensuring that the data information loss should not happen. We can use dimensional reduction techniques, some of them, and then ensure that we can compress the data, and we can regenerate also using the inverse transforms, which is available already in the scikit-learn in Python. There we can ensure by certain amount of variance we can fix, which we saw earlier, by ensuring the data compression can be possible. Noise reduction is one of the key other feature. We want to ensure that the SNR ratio, signal to noise ratio, should be intact. Data classification, which we saw as an example in t-SNE, we can see certain clusters and we can classify certain particular data points. From the bioinformatics or biosciences or bioengineering perspective, people use in genomics a lot these kind of techniques. And the first step, because in the genomics, is to always ask that is there any kind of an inner hidden structure, what we are trying to target with our genome, which we want to really decode? Is it really clusterable? Yeah. So PCA definitely, along with other non-dimensional, non-linear dimensional techniques, is useful, and we use it a lot in aerospace domain, in mechanical sciences in general, which includes mechanical engineering, civil engineering, EC, and a lot. And then obviously the field, the new jargon which we all are part of is in machine learning. We use it in we extract the information by ensuring the information should not be lost. However, to all the engineers and scientists and research community, let me give you a word of caution before you really start jumping on using the dimensionality reduction techniques, which some of them which we discussed today. Reducing dimensionality does lose some information, right? So, so even though it speed up your training, it may also make your system perform. Please focus on this, perform. So I'm talking of performance of the algorithm, performance of the system, accuracy, and many other parameters around that. It can become worse. So please be cautious about it. So what you should do, right? What you should do is it can make your the data pipelines and a bit more complex and harder to maintain. So what you should do, what you should first try to train your system with the original data as it is. I know it's going to take a lot of computational time and infrastructure, but that is the advice, recommendation which I want to give it to you before considering using dimensionality reduction if training is too slow. Yeah? In some cases, however, reducing the dimension of the training data or the training matrix X, feature matrix X for the training, may filter out some noise and unnecessary details and thus result in higher performance. But in general, it won't. It will just speed up training. So the key message I want to leave you, don't jump directly on reducing the dimension and start working with time series data, because the output of PCA will go into your input to your regression or time series algorithms. So directly don't jump into that, because some of the key critical information will be lost. So evaluate that, validate your data, right? With the first, without reducing the dimensionality. Yeah. All right. Now let me enter into the third part of the presentation, which is the demonstration using visual mathematics and some recommendations from my side. So, sorry. Okay. So here you can see the three particular equations. Yeah. So and also the corresponding graphs for that. So the red one is the sinusoidal curve. The blue one over here, the light blue, is the first V1 vector, and the black dotted line is the cosine curve. So this data is a generated data to show the visual representation and inferencing out of it. So this is the loading figures, or known as also biplots in the PCA. So if you see that, so here you start getting certain vectors, which are the principal components. But let you experience that in the real time. Okay, let me switch to right. It is firing up. What I'm going to show to you is the loading plot for the PCA with these particular three functions, V1, V2, and V3. And here it is. Are you able to see this, Professor Geeta?
Yes, sir. We are able to see it, sir.
All right. So now, if you see it over here, now I can change the phase interactively. Little slow, so pardon me for that. Yeah. Now, by changing these particular three entries over here, if you can see that the function is changing. Yeah, because here the phase comes over in the first function, and by changing that phase, if you see, if you see from the mathematical construct which we discussed earlier in this second part of the presentation, the basics of PCA, I'm changing the covariance matrix, right? Which here I'm calculating the covariance from there, and then that is actually getting changed. And then the whole idea is we want to preserve the variance, right? Remember, as I said, the thumb rule is the 95%. We want to preserve the variance around that. We can see interactively that when we change the numbers, how much is the contribution of the variance from these three particular dimensions which we are getting. And if we want to really reduce it to two-dimension case, right, in the 2D Cartesian coordinate system which we have over here, then can we really get rid of the third dimension? That's the whole idea, right? So we can really play with that to understand it interactively. What is happening over here when I change the particular function and the contribution of that particular function, how does it going to contribute to the variance, and then how much variance I want to preserve, and then what is going to happen to my reduced dimensional system. So this is the whole idea that, rather than just working with the plain, what I say, pure or applied mathematics both, we need to work and give this particular sense to the educators, scientific fraternity, that we have to work in the visual format of the same thing. And fortunately now there are very interesting and doable or applicable mathematical scientific computing routines and languages. So this is a plot which I have developed in Mathematica. So some of you, or if you really are interested in that, I can share some of the work. We can work around that. So this is the key critical information. Now let me give one very interesting demonstration on the visual data, as I promised earlier. And I would like to let you appreciate that if we visualize the data in 2D or 3D or in 4D, as we saw in Tesseract, please appreciate that data visualization is not just plotting. Let's see that. What do I mean? I'm going to let you observe something very fascinating, which you shall remember for many, many years from now on, from the context of visual mathematics and visual statistics by Professor Hans Rosling. He's no more. He was a Sweden mathematician, and he worked on something very wonderful work and literature, and he wrote a book on factfulness and what I call let the data sing. Yeah. What we are going to see now, 200 countries spanning in 200 years in 4 minutes, and let's enjoy the stats.
Is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space, with a bit of technical assistance from the crew.
So, here we go. First, an axis for health, life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle, but there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa.
And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With aid, trade, green technology and peace, it's fully possible that everyone can make it to the healthy, wealthy corner.
Well, what you just seen in the last few minutes is a story of 200 countries shown over 200 years and beyond. It involved plotting of 120,000 numbers. Pretty neat, huh?
Professor Hans Rosling has also developed a software known as Gapminder, which was in 2007 acquired by Google during his TED Talk, just during the, this was so impactful. So if you really do your job well, you can really be picked up by the best. Yeah? So now let me, in the interest of time, give my last thoughts in the third part of the presentation about future research and technology. As I said, we have to move now from research and development to research and technology, R&T. And here are my recommendations. We should not chase the unicorns. And I'll quickly show you the knowledge triangle, which I have developed. And then we should work more on the probabilistic side and the causal analysis. So here I want to show you quickly that this is the trade-off diagram, right? So here, some of the people who really interview and also want to hire some research staff, they always say that I would like to look for people, those rare individuals who excel in all these areas that encompass data science, analytics translator, data scientists, they are data engineers, and even they should be data visualization experts as well. So indeed, I mean, they're looking for unicorns, right? This is a picture of a unicorn over here on the top right corner. It's a fictitious, character. Unfortunately, unicorns don't exist. And even if they do, it's not worth chasing them. So the best strategy should be that you should build data science machine learning research teams with complementary talents. That's why these days you will see that the people who are entering into these AI, data science, machine learning fields, they are from different streams of engineering, different streams of arts, different streams of biology, and many other streams. So it's not only a field which is from the mathematics community or from computer science community. So complementary skills are welcome. So, but why complementary skills should be appreciated, and why then we should do the core areas such as mechanical engineering, aerospace, ECE, computer science, and likewise. So here is the answer to that, what I call as a knowledge triangle. Yeah. So some of you who are from aerospace domain, you might refer to this as aeroelasticity figure from Bisplinghoff. So here what I say is, these each circle represents the key areas where you specialize. If you really focus on, which is a 10,000 hour rule, if you really do spend 10,000 hours dedicatedly, then you became a domain expert, let's say aerospace engineering, which is my domain, and then you can become a domain specialist. However, if you really do well in that, you can become an algorithm or research scientist in that domain, right? You can flourish in different domains and can be called by different names, but essentially you become a scientist, a research scientist, right? Then if you are from software engineering or scientific computing community, you can become really good into Python or a particular language, programming language, all right? You can be a good data engineer, big data engineer. You can become an app developer. You can become a UI UX specialist. However, if you combine any of these two particular circles, then you can become what is written on the sides of this bilateral triangle. If you combine domain specialism with the applied mathematics, then you can fit into an engineering and technology team quite well, right? Which was generally earlier the scenario. If you really combine the applied maths with the software engineering skill, then you can become a really brilliant data engineer or data scientist, or AI scientist for that matter. However, if you combine domain specialism with the software engineering, you can become a good business analyst or scrum master, which is a term which is coming along these days. However, if you see that, I have worked for more than 11 years in these domains, and what I realized that it is the key thing from a structure perspective. These are the three key legs. So n is equal to 3 is the minimum critical number. Without that, system is not stable at all. So from that perspective, if you really don't know your domain, the people who are good data engineer or data scientists, they really fail to comprehend and tell your system to your clients, to your research boss, right, to your research team, to your, when you really need to write and describe that to a research community in your research article, then also you need to be good in your domain. So the key idea is, if you really are good in the domain and then you earn these skills, then you really become very solid data scientist. However, if you are from computer science already, then definitely that's your forte, right? You really work on algorithmic side, or you can learn the domain by working collaboratively, as I said earlier. So you work with complementary talents. But what I want to appreciate and let you appreciate that is that the domain specialism is the key, guys. I mean, if you're working in a particular area such as aerospace, mechanical, civil, ECE, or likewise, then you are at really at the forefront, because you know something critical where you can add on these skills, right? The people who are already in the computer science, they are strong and they can become good into the algorithmic side, right? So it's like a handshake as a win-win situation. You have to really judge yourself and appreciate your domain. Don't leave your domain, right? Upskill yourself. All right, let me give my second recommendation. As from the mechanical engineering community, we all are aware of, if you take a particular dimension, and if I have to tell you that the diameter of a particular cylinder is say 5 millimeter, that's actually wrong. We have to always give the tolerance limits, the 5 millimeter plus minus the 0.002 or likewise. So the idea is that the world which we live in, the work which we do, it's actually not deterministic. It's not deterministic. It's probabilistic. So if some of you who really are interested in working into the field of machine learning and also in your own domains, you should start working and reading these particular literatures and work on more on the probabilistic side. That's going to lead you into the future. And the last thought I would like to leave you with is that, don't focus on the correlation. This is the key thing which sometimes I feel and I always observe while reviewing some research articles from the global community. People start giving so much of emphasis on p-values and correlation blindly. However, as an engineer, as a scientist, we should always ask that, is it really the reason of causation, right? So if you see this cartoon that sails and shaved heads are correlated, but that doesn't make sense, right? So there's a wonderful literature by Professor Judy Apple, who is the pioneer of this whole idea of causation. Can you please go through that? To end my presentation, as I promised, I'm going to address these questions, which we have already observed. The fourth dimension, can you visualize it? Yes, we can visualize that. We have seen in Tesseract a 3D projection of Tesseract performing a double rotation around two orthogonal planes. The second question I asked was, Carl Pearson, father of statistical mathematics, how he is related to dimensionality reduction. He is the one who has invented PCA in 1901, right? So definitely it was rediscovered multiple times in many fields. All right, so here's the end of the presentation, and I make complex easy, please. That's the responsibility of all engineers and scientists alike. And thank you for giving me this opportunity. And all of you are encouraged to interact with me and in any of the, and give me the feedback to further improve and also share your thoughts and collaborate.